Welcome to this video series on Galois theory. The purpose of this video will be to casually introduce field automorphisms. And what I want to do is motivate the usage of these guys in our subsequent study of Galois theory. So classically, Galois theory has been about polynomials and their roots. It's been about certain patterns and certain symmetries in the roots of those polynomials. So this is what, at least for classical applications, we're interested in, polynomials and their roots. That's what classical Galois theory is about. But a lot of the time, and in this series in particular, we won't spend our time explicitly talking about polynomials and their roots. Instead, we'll spend a lot of time talking about something called field automorphisms. And the reason for this is that field automorphisms are a tool which will help us understand polynomials and their roots. So by using field automorphisms, we'll be able to accomplish our original goal of understanding polynomials and their roots. So what I'd like to do in this video is begin convincing you that this is a good idea, that field automorphisms are a good tool for studying polynomials and their roots. Now as we go along, we'll see a lot more kind of impressive applications. It'll become more and more apparent that field automorphisms are a good idea. As we build up some theory, we'll see that symmetries in the roots of polynomials are nicely expressed through field automorphisms as symmetries in certain fields, whatever those are. So as time goes on, we'll get more and more impressive reasons why field automorphisms are a good tool. But I think it's nice to have, right from the outset, a kind of convincing example in mind. A convincing situation in which field automorphisms really show their power as a tool for studying polynomials. So the motivating example I have in mind is the following fact. The fact is that the roots of real polynomials come in complex conjugate pairs. So this is a fact, this statement is true, and this seems like a statement which is totally about polynomials, right? We're just discussing real polynomials, and we're discussing their roots. But it turns out that field automorphisms will give us a nice way of seeing why this fact is true, and that's the motivating example that I want to give. So let me first formalize this fact, and we'll formalize it as follows. Let's let P be a real polynomial. That's what this notation means. And saying that P is a real polynomial, all that means is that we can write P of x is equal to C0 plus C1x plus ... plus Cn xn, where Ci is a real number for all I. This is why we say a real polynomial, because all of these coefficients, Ci, are real numbers. Okay, so let's let P be a real polynomial, and let's let zeta be a complex number. Then P of zeta is equal to 0, if and only if P of sigma zeta is equal to 0, where sigma is complex conjugation. So remember, complex conjugation is the map that takes A plus B I to A minus bi, where A and B are real numbers. Every complex number can be written of the form A plus bi, with A and B real, and assuming that form, complex conjugation is the map that takes A plus bi to A minus bi. So algebraically, this statement means that P of A plus bi is equal to 0, if and only if P of A minus bi is equal to 0, again letting A and B be real numbers. And geometrically, what this is saying is that if we draw the complex plane like this, where we have the real axis down here and the imaginary axis up here, geometrically, what this statement means is that some point in the complex plane is a root of P if and only if its reflection across the real axis is also a root. That's just expressing the same thing. So before we try to prove this claim, we should try to validate it empirically, right? We shouldn't take the claim for granted. It's always nice to see the result is true with a couple of examples. So according to this statement, it should be the case that a plus bi is a root if and only if a minus bi is, and it should be the case that the roots are distributed symmetrically across the real axis. So let's look at a few explicit examples and see whether this is actually true. Let's see whether the claim actually holds in practice. So let's go to Wolfram alpha, and we'll ask it to compute the roots of some random polynomials for us. So maybe we'll put in some polynomials that we like and see what the roots are. So let's compute the roots of x squared plus x plus 1. And we see that there are two roots. There's half plus something times I, and there's half plus negative that thing times I. So it was the case that a plus bi was a root if and only if a minus bi was a root. And then looking at this picture, we see it's true that the roots were distributed symmetrically across the real axis. So that's one example. Let's try a different polynomial. How about x to the 17 plus 23 times x squared plus pi. That's a real polynomial too. And let's see what its roots look like. Okay, so there's one real root, and the conjugate of that is itself, so it trivially is true that the conjugate of this is also a root. And then we have some complex roots. And here we have a minus something times I as a root, and then a plus that same thing times I as a root. So we just switch the sign of the I coefficient here, just like we would expect from the statement. And similarly for this pair of roots, these roots are also complex conjugates. And there are more roots here. We can look at them, and they all satisfy this property. This a plus bi is a root if and only if a minus bi is a root. Looks like we're missing some at the end here. What if we keep asking Wolfram alpha to give us more? Yes, so now we see. So they satisfy the statement. And when we look at the graph, we see that the roots are indeed distributed symmetrically across the real axis. So let's try this with a couple more. Maybe we'll do one more. How about e times x to the 4th minus 15 times x squared minus 1/2 times x plus 2. So all of the roots of this guy ended up being real. That wasn't that interesting. Let's try changing the sign of one of the coefficients. Good. So again, we had 4 roots. These two guys are complex conjugates, and these two guys are complex conjugates. This is a plus bi, this is a minus bi, and then this is a plus bi and a minus bi. And again, the roots are indeed distributed symmetrically across the real axis. Okay, so we've seen that this statement has a chance of being true, this statement here, because we've done some concrete examples and seen that it holds in those examples. So now let's try to understand why the statement is true. And I claim that field automorphisms will give us a way of doing that. And here's why. The 4 listed properties are true of complex conjugation, and we'll see in a minute that these 4 properties are exactly what we need in order to see that the roots of real polynomials come in complex conjugate pairs. So I'll briefly discuss these 4 properties, and then I'll show you why they imply that the roots of real polynomials come in complex conjugate pairs. Alright, so I claim that complex conjugation has the following properties. First, sigma of 1, where sigma is complex conjugation, is equal to 1. So we say that sigma fixes 1. Alright, second, for all complex numbers zeta and omega, we have that sigma of zeta plus omega is equal to sigma of zeta plus sigma of omega. So we've moved from an addition inside the parentheses here to an addition outside of parentheses. And the way this property is usually expressed is by saying that sigma commutes with addition. And similarly, we have that for all complex numbers zeta and omega, that sigma of zeta times omega is equal to sigma of zeta times sigma of omega. So here we had multiplication inside the parentheses, and here we moved it outside. And the way this property is usually expressed is by saying that sigma commutes with multiplication. And finally, we have that for every real number r, sigma of r is equal to r. And this is usually expressed by saying that sigma fixes r. Now, of course, because 1 is a real number, this first property is kind of redundant, right? It follows from the fourth one. But in general, when we talk about fuel automorphisms in general, it'll be nice to have these things laid out separately. All right, so maybe I should just say how these four properties are bundled. These first three are saying, and we'll see this later, I'm just sort of explaining some terminology which will come in later videos, but these first three properties are expressing the fact that sigma is an automorphism of C. And we'll see what this means more in later videos. This is just a special example of a more general definition. And this fourth property is saying that sigma fixes R. I've already said this. So in total, these four properties tell us that complex conjugation is an automorphism of C, is an automorphism of the complex numbers, which fixes R, the real numbers. So sigma is an automorphism of C which fixes R. Now, I'm not going to prove these four claims, but they're not that difficult to verify. So I encourage you to take a moment to check that they're true. All right, so now let's see how these four properties give us what we want, how these four properties imply that the roots of real polynomials come in complex conjugate pairs. So let's let P be a real polynomial. So let's write that P of x is equal to C0 plus C1 x plus ... plus Cn xn. And remember, because P is a real polynomial, we have that the Ci are inside of R. The Ci are all real numbers. Okay, and let's let zeta be a root of P. The root of P. So that just means that P of zeta is equal to 0. Now, we want to use these properties of complex conjugation to see that sigma of zeta must also be a root, that the complex conjugate of sigma is also a root of P. So why would that be true? So we know that P of zeta is equal to 0, and we want to show that P of sigma zeta is equal to 0. And the trick here is going to be to consider sigma of P of zeta. Now on one hand, this is equal to sigma of 0, since P of zeta is equal to 0, which is equal to 0. But on the other hand, sigma of P of zeta, well, let's write it out. It's equal to sigma of C0 plus C1 zeta plus ... plus Cn zeta to the n. And now we can start using the properties of complex conjugation. So we know that sigma commutes with addition. That was property 2 over here. And what that tells us is that sigma of this sum is equal to the sum of the sigmas of the individual parts. So let me write that out. So this is equal to sigma of C0 plus sigma of C1 zeta plus ... plus sigma of Cn zeta n. This is because sigma commutes with plus, with addition. Okay, but we also know that sigma commutes with multiplication. So this is equal to sigma of C0 plus sigma of C1 times sigma of zeta. So we expanded this out, and plus ... plus sigma of Cn times sigma of zeta to the n. Notice that we move the exponent to the outside here. And we did that using the fact that sigma commutes with multiplication. So here we got from this part to this part by saying that sigma commutes with multiplication. Now, let's use the fact that sigma fixes the real numbers. Remember, all of these Ci are real numbers. So sigma fixes them. Sigma of Ci is equal to Ci. So this is equal to C0 plus C1 times sigma of zeta plus plus Cn times sigma of zeta to the n. And this was using the fact that sigma fixes R. But what is this last guy? This last guy is just equal to P of sigma of zeta. So P of sigma of zeta is equal to sigma P of zeta. And we know that sigma P of zeta is equal to 0. So P of sigma of zeta is equal to 0. And that means that sigma of zeta is a root of P. So we've proven that if zeta is a root of P, then so is sigma zeta. That is, if zeta is a root of P, then so is its complex conjugate. So we've shown that P of zeta is equal to 0 implies that P of sigma zeta is equal to 0. Now to go in the other direction, to get the implication that P of sigma zeta is equal to 0 implies that P of sigma is equal to 0, you need to use the fact that sigma is a bijection. Or you can use the fact that sigma squared is equal to the identity. That is, sigma of zeta is equal to zeta. Either one of these facts will help you prove the converse implication, that if P of sigma zeta is equal to 0, then P of zeta is also equal to 0. And I will leave both of these as exercises.